Sure. So I'm Frederick. I am one of the committers of Network Service Mesh. Nikolay is a committer. We also have in the room, at least I saw him earlier, Ed. He's in the back. Ed. So feel free to talk to any of us after the presentation. And so we're going to go over a deep dive of Network Service Mesh. So we're going to go over the architecture, and we're also going to go over the SDK that we worked on, so that if you want to build what we're calling a CNF, so if you actually want to build something with it, we're trying to make it as easy as possible.
Uh-huh. So we're going to show a little bit of YAML files on the screen. I hope that they're going to be seen good. And slight reduction of our Go code that you can use to enable Network Service Mesh for your applications. We try to make it not look that scary. So we're going to go through it. And Fred, you're on.
Great. So Network Service Mesh, so we start off with what is a network service? So in Network Service Mesh, we have three core concepts. We have something that wants to connect to a network service. We have something that provides the network service, and we have something that we have the connection between the two. So a network service is anything that you want to connect to that provides a service for you. We specifically look at layer 2 and layer 3 services. So if you're looking for an L4 or L7, then kindly ask you to take a look at the application service meshes such as Istio, Linkerd, and so on. What we're focusing on specifically is L2 and L3. So if you have a Ethernet or an IP payload you want to pass, then this is the place to do it.
Although in the end we're going to show an example that actually contradicts a little bit this statement and shows how you can use higher level protocols with NSM also.
Yeah, we can connect you to things that provide those higher protocols. So, yeah. So we start off with a gRPC API as well. So we don't show off the gRPC API in this presentation, but all the connections, everything that is part of the dynamic live system itself, you can do through gRPC. And so this means that if you want to hook in something like, we're starting with Kubernetes, but if you want to hook in OpenStack or you want to hook in a physical system, then you use the gRPC APIs, and you can then connect things that are not part of Kubernetes. The system is also distributed, so there is no centralized control plane in this scenario. It's purely distributed. We do have some patterns that we recommend. If you have to do something with some centralized information, you can centralize that to a specific system, perform the work you need to do. But inherently, it is a distributed system at heart. And we also provide a concrete Kubernetes-based implementation. So this implementation we're calling it at the moment our reference implementation. It does not touch your Kubernetes networking. It is orthogonal to CNI. So we also leverage etcd as a central shared storage. So we actually create CRDs and we store information about where the network services live with that. We deploy using daemon sets. You could do like helm install. And we also used in our reference implementation, we use VPP, which was kindly provided by the FIDO and LFN community. Just to note though, VPP is not a strongly required element. So for the reference architecture, we add it in, but if you want to put a different data plane underneath of it, as long as someone implements the gRPC API to do so, then it should be trivial. And the API is very simple.
And we actually have in the room one of our contributors that is working on enabling Linux bridges for this.
So let's start with what Network Service Mesh is. So we start off with in the system we have a Network Service Manager. So and this is a daemon that stores that is actually doing the actual facilitation of the connections themselves, and we store the pointers to each of those within the Kubernetes registry itself. So we know where each manager lives. We have a registry of network services. So this is so you create your network service in a pod. They then get stored in the location of those or rather not the location, but the definition of those gets stored in the registry. So this includes information like what payload is it? Is it like an IP or is it Ethernet or MPLS or so on? And we also have the endpoints, which are the things that actually provide those services. So it's very similar to Kubernetes, where you might have like a service that provides a web application, and then you have a set of endpoints that actually provide you the real thing. So we have the same thing. We have a network service that provides you with a description of what the service is, and then we have endpoints that provide you with the actual connectivity. And so once we have connections where you can see like a network service client itself, through, with some context, we show off a little label on the bottom left. So with this label, with these labels, we can also provide additional context that gets set at runtime. And it allows us to connect pods of, you notice these are going directly from client to endpoint. So everything here is point to point. So if you want a subnet or you want a bridge domain is like think of it like a switch, then those are network services. So you are connecting to a network service, to a subnet. So what this ends up looking like, if you're trying to define a service. So one of the examples that we've shown in the past was the concept of like how do you connect to a VPN. So if you think of what it takes to connect to a VPN, you want to have a pod connect to let's say corporate to secure corporate internet. So that pod, the operator may decide, okay, this pod must go through a firewall, must go through an intrusion detection system, goes through a VPN, client, and gateway, and so on. So this entire list of things, this entire chain is specified by the operator. So as the consumer of this VPN, you shouldn't have to care about any of that. You shouldn't have to care about, does this thing have a firewall? Because your operator is taking care of that for you. All you care about is, I can connect to this thing and it works. And so this is one of the areas that we have where if you see, we have a source selector. So this actually specifies two endpoints that we're looking at. So one of them is if a default match. So when you connect in, the default match is empty. We have a route to a destination. The destination says app firewall. So that's actually the bottom one. Maybe I should come around so I can point it out. So yeah, so you can see the destination right here, match route firewall. And then the firewall, when firewall connects to the network service, so these are all composable. So when the firewall connects in and says, I want to connect to secure internet connectivity, then it says the source is firewall, the destination is then VPN gateway. So you can create arbitrary chains of your network services in this way. So as an operator, you're defining in a declarative way what your system is. Things to note about this as well. There's no IPs listed here. There's a payload. Payload is set to IP, but we're not putting any MAC addresses. We're not storing anything about the runtime on a scenario. That all gets there's still IP addresses. There's still IP addresses. There's still MAC addresses, et cetera. But they're part of the negotiation when you establish the connection. And so what this ends up looking like for our particular system, if you're the user who wants to connect, so notice this one is a deployment and it has a pod spec inside of it. So this one's just running Alpine, and in the metadata we added in an annotation. In that annotation is ns network service mesh.io, and the name of the service that you want. That service, you could be secure internet connectivity, like as we had before. The label allows you to provide additional context, additional information. Our recommendation at this point is if you want to add in a label, the label should be something that is at a high level, that's declarative, not something that's low level. You should not be adding in, this is the VLAN ID, or you should not be adding in specific VXLAN data or that kind of stuff. So let that be done at a lower level, at the operational side. And so if you include this annotation, then we have an admission controller. And what this admission controller does is it injects an init container into your pod, and that init container will then use the SDK that Nikolay is going to show in order to make the connection. Something that we're able to do as well is, this is for like a standard legacy, well, I'll say legacy, we'll say it's a standard application. If you want to hook in something that has more intelligence, more complexity at the network layer, you could also use the SDK directly you don't have to bring in the init container while the application is running. You can ask for things. So if you want to say, I want to open up a firewall, or I want to open up a connection to my secure banking information, and start, or find my financial network and start to make some operations, and you want to close that to minimize your risk, then you can do that. If you're building out, if you're one of the service providers and you want to build out more intelligent networks that are based upon the actual conditions of your system, then it gives you the capability to do so. So the way that this works, I compressed this a little bit from the operational side, is in the client, when you make a connection, so these black lines are all gRPC. So we make a connection request out. And in this connection request, we say we would like secure internet connectivity, and that gets resolved to a VPN gateway pod. And so we say you request connection. So in that request connection, we also include information like how do I want to connect to this thing? So it turns out that there's more than one way. You can use more than just kernel interfaces to connect to a network. So you also have things like memif, vhost user, and these are kernel bypass mechanisms, ways to get to your data plane very, very quickly without incurring the cost of the kernel. And so if your pod is more intelligent, it could say, I support memif, vhost user, kernel interface in that preference, and that all gets wrapped into the request and gets sent up to the NSM manager. The NSM manager will take that particular request for the network service and forward it on to the pod that's providing the service. And the pod can make a decision. Do I want to accept this request, or do I want to reject it? Maybe there's something about it it doesn't like, or maybe it can't handle the request anymore. So it'll respond back with whether it accepts or rejects it. So let's assume that it accepted. Then it'll create the interface on the right side, create the interface on the left side. It'll then configure your data plane based upon what it knows about what it negotiated here and what it negotiated on the other side for their local, what we call local mechanisms, and then it performs the cross connect. So this is for the single node example. The multi-node example is similar. So multi-node example, we have a request connection with that local mechanism as we had before. It'll connect to the CRD or to the Kubernetes API server to work out which network service manager do I need to connect to in order to gain access to that system. So once it knows, oh, it's NSM manager 2, it'll then send that request over to the NSM manager 2. Now this additional request, step number 3, has some additional information it added it. So this information is about what remote mechanisms that this data plane down here supports. So you might even have 2 different data planes from 2 different groups. So this data plane might say, I support VXLAN and GRE, and we'll send that in the request connection. Step 4, that information gets stripped out, but it's still stored off to the side. And the request, like before, gets sent to the VPN gateway, so that path is the same. When it accepts, we create and inject the interface on the right side. We then create the tunnel with the data plane. We create the tunnel on the right side, and the data planes will then. So now we have the tunnel created, we now have some more information that we can then pass back. So maybe the data plane selected. We decided to go with VXLAN with these parameters, so that way you can have your tunnel. So that gets encoded in the reply. So when the reply returns, NSM Manager now has all the information it needs in order to make that connection. So the interface gets injected in with the mechanism requested. Then this side of the tunnel gets created using the information that came from the reply. And once the tunnel is established, we respond that the connection is ready, and then now you have a full working connection. So we use this pattern over and over and over again in order to create and connect the network services. Before we move on, are there any questions on this? Sure.
How do you inject the interface? Are you using standard CNI?
No, so we don't use CNI in this scenario. So CNI is tightly bound to the life cycle of the system, and CNI also is missing. I won't say missing. CNI was designed for a very specific reason, which is I want to get IP connectivity to a network. And so when you start to look at other systems, like what does it mean if you want to be an entire L2 payload or so on, it doesn't really make sense in that area. The other advantage that we have is that when we establish a connection, we're not part of the life cycle of Kubernetes other than the pod can make a request. It's part of a pod for this example. So when you start CNI starts before the file system is established. And I know it sounds weird talking about file systems here in a networking talk. But what happens with is if you want to add in shared memory, so you want to do kernel bypass, you have to be able to mount an inode somewhere in your file system so you can then access it. Since you have no file system when CNI is running, you don't have anywhere to put it. You do have access to a network namespace, so you can inject kernel interfaces, but you cannot easily inject a shared memory interface into the system. So because of that limitation, that required us to provide an alternative path in order to establish those in. So that's a good question. Sure.
How do you support the network policy?
So Kubernetes network policy is not something that we're providing in this. So we're orthogonal to Kubernetes networking. You can have policy, but your policy would get encoded into the network service, or you provide a policy through a network service. So like you can have a firewall, and that firewall could implement your policy for you. But we're not reading directly off of Kubernetes policy because it's an orthogonal network to it. I saw one in the back over here.
What kind of permissions do you need?
What kind of permissions? Unprivileged. So the injection occurs with in coordination with the network service manager and the data plane, which have a little bit more. The data plane doesn't have permissions, if I recall anymore. So we actually managed to get rid of that. So we delegate. When we make a request from this init container, there's no permissions. It gets injected in through something that the user does not have control over, other than the ability to make a request for a connection. Sure.
Can I have multiple interfaces?
Yes, you can have multiple interfaces.
So in terms of CNI, basically we can use whichever CNI we like, and we just say that establish one of the Kubernetes primitives, which is pod-to-pod connectivity, and then we use this to enforce layer 2, layer 3 segregation. And we have a catch-all rule which says deny everything that's not explicitly allowed, yeah?
So in terms of the CNI part, so we go to great lengths to not interfere with the CNI. So Kubernetes networking is very well done. We don't want to mess with that. Simultaneously, anything that it's up to there is some part in the application in terms of how you set up the routes and so on. And those routes, like it depends, if you're a VPN gateway, you'd provide those routes and those would get injected in, and then those would then head off. So as an operator, you do need to be slightly concerned with some of this stuff, but it's a lot easier than the current state. Because the current state, as you said, is you may end up setting routes globally at a high level. And in this scenario, we can negotiate that, and we could set up a policy that says if the routes conflict or there's some confliction, here's how you resolve it, or fail the connection, or so on. So as an operator, it should make your lives easier in that respect. Sure.
How do you solve the scale out problem, basically? I mean, as you scale out, you are getting a time spread problem in this function of panels, right?
Okay, so this is a little bit of an interesting area. So in terms of scaling out, so first the actual NSM managers themselves are point-to-point systems. So each of these connections is point-to-point. So are you thinking like VXLAN where you might run out of like parameters or so on, or are you just thinking about managing lots of stuff?
Services there, I only see cost, but I don't see services.
So.
I see scale out cost.
Well, the gateway pod is a service in this scenario, and so in terms of scale out, we can scale out the number of pods that you have. So like instead of having a single gateway, you can have multiple gateways. Or instead of having a single firewall, you can have multiple firewalls. And when you do the connect, and then we can, based upon some mechanism, we can then select one on your behalf and connect you to it.
But it's like a lot of churn in terms of scaling, right? If you are auto-scaling up and down, you have to create a lot of panels and then turn them.
Well, the good news is the tunnels are cheap. So what's more expensive is if you try to set up like if you try to set up let's say a vSwitch or something, like running it all through a vSwitch. vSwitches are very expensive. They're very computationally expensive. In this scenario, we're just doing very simple point-to-point connections, and point-to-point connections scale out very well. Like the entire internet is built on point-to-point connections. So from a scalability perspective, like this entire system is distributed. We're able, if you get to a hyperscale scenario where like you don't want to list out where is every NSM, where is every gateway pod. When you get to a hyperscale, we haven't implemented this yet, but you could go and do something like summarization or something similar. So that way you say, here's one particular system, then you let the backend system resolve, which is very similar to how DNS works today. So when you hit DNS, it'll give you back an endpoint. It won't give you like all the endpoints of that an area may exist with. Sure.
To create connection, you need to do some about 11 steps, and it's probably takes some while time. You need to do every time you set up connection.
Do you remember how long we benchmarked it? How long the connection took? It was milliseconds at the most for establishing a connection.
Like persistent down, or it's every time?
Yeah.
No, there's no.
Yeah, this is more on the persistent side. So it's not like you're making a connection, making a packet closing connection. So you establish a connection, then you now have this is an L2, like an L2 L3 connection, not like an L4 or L7 connection. So once you've established it, like it might be a connection to your gateway pod, and then you just send everything over it. So I want to make sure that Nikolay has time as well to go over his stuff as well. But
we're running a little bit out of time.
What's that?
We're running a little bit out of time, like 10 minutes.
So I'll go ahead and let Nikolay continue.
Yeah. Okay, so all these details are interesting, and I'm sure that people that want to port Network Service Manager to and the whole NSM architecture to other platforms, like integrate with OpenStack and the likes, they would be interested. But if you are a regular developer, so you don't really care about these things. So at last KubeCon, we sat down together as a community and we started thinking how we can expand our examples, and that's when we came up with the idea of the SDK. So one way to actually do consume network services within NSM is implementing the so-called smart client. So whatever Fred showed a couple of slides ago with the admission controller is like injecting the init container. This gives you some flexibility to use your to actually enable NSM for your existing applications. But if you want to do something smarter, you want to be able to control your connections to the network services, you should use the SDK. And this is how it looks like. So essentially there are three or four actually calls. So the first thing is you create a new NSM client, then you call the connect method with a couple of arguments, the interface name that is actually going to be injected in your pod where the application is running. The next argument is the type of the mechanism. So currently here is shown kernel, but you can use the other mechanism that we do support, as Fred showed, vhost user, memif, and whatever appears in the future. And then we have some small description just for logging purposes, saying things like, okay, your primary interface got connected. Then as a result of this call, you essentially get a connection structure. So this is a dump in our Jaeger, where actually you can see, because remember all these calls within the SDK actually are hiding our gRPC communication. So we have Jaeger enabled all over the NSM infrastructure. So when you look at the messages, this is essentially what you get as a result of this call. So you have all the information. In this specific case, we have requested the services IP enabled. So that's why the endpoint, the network service, essentially replied with all the IP addresses, routes, IP neighbors, filled in, all the data is filled in the context. So getting this, so what we see here is we have the source IP and the destination IP. So the source IP, within network service mesh, we call the source the requester of the address. So in this case, it would be the client. So this means that your local address that you get is 1061.1, and the remote address of the point-to-point connection is 1061.2. This is just for information reasons. I mean, you don't have to do anything. You just can use this information to implement your functionality. The interface is injected in your pod, and all the IPs are set, all the routes are set, everything is in place. Our tables are updated, and etc. So this is all done through the SDK. So when you get this information, you can actually run your actual code. You can do your, you can consume your service. You know where the other end is, and then in the end you can close the connection. You can open it again if you need, and when you're done, you just call client destroy, which is in the bottom. I didn't highlight it. So this way you have a dynamic control at the runtime of injecting interfaces actually within your pod. So you request an interface, you request a network service. As a result, you get this interface injected for you. The service is there. When you're done, you can close. The interface gets removed. You can request it again. You don't have to restart pods and do things like that. Clients are fun, but I guess that a lot of people would be interested to know how you implement a network service endpoint. So here is an example with where we have a network service which is composed of 2 endpoints and 1 client. The 2 endpoints are pod 2 and pod 3, and the client runs in pod 1. So let's quickly look at how this works. So essentially, client requests a connection to the network service. It gets the connection to the first pod within the network service, the first endpoint, which would be running in pod 2. And then on its own, the network service point in pod 2 requests a connection to the network service endpoint in pod 3. This is how one option that you can implement network service. You can do this with static connections, like at the moment that the 2 endpoints are deployed, they connect to each other and just wait for connections. Whatever we are showing here is just a dynamic mesh establishment upon the request. So imagine that your endpoints are just sitting there, being deployed, sitting there waiting for connections. Once the client comes, and depending on their request, they can dynamically establish the mesh. So you don't have a static connections all over established all the time. But this is one option. I mean, you can do whatever works for you. So essentially, if you zoom in a little bit in the network service endpoint in pod 2, what it has to implement is it has to handle the request from pod 1 and then generate requests to pod 3. Now let's see how this works in the code. So this thing looks probably slightly more complicated, but it's really not. So the orange highlights are showing the calls to the SDK, which are related to the implementation of the endpoint. So you first have to we have this notion of composites. So the composite is essentially a chain of structures which implement callback-like interface. These structures we call composable. So these are the green highlighted calls. So the first thing that you do is you create your composite, then you create a new network service mesh endpoint where you pass your composite as a pointer there, and then you start the endpoint. As you can imagine, the start function is just blocking it, sitting there, waiting for connections to happen, and passing all the incoming requests to the composite. Now, what actually the composite looks here? So we have stack of functions. So on the top we have the monitoring function, which essentially just waits for all the incoming connections and then updates our monitoring mechanisms with the creation and removal of new connections. This is useful for observability, for monitoring. You can imagine all the things. Then we chain this to an ACL, which is for those that you don't know, is a access control list. It's a simple form of packet filtering. We chain this to a function called cross connect. As you as we showed on the previous slide, pod 2 essentially sits in the middle between the client and pod 3. So what it has to do is it just has to connect the two interfaces that it has. So that's what we do with the cross connect. Then we have a network service client, which is essentially the layer that generates the request to pod 3. So this kind of generates the request for the next endpoint. And at the bottom we have a simple, this is a layer that just creates and fills structure that we need. Actually, this is the structure that we showed in the client that has all the IPs and the context and stuff. Now, if we zoom in a little bit in the requests, not in the requests, but in the composables, this is what we have. So the request callback, essentially, when you get the request, you can use it or manipulate it, and then you call the next guy in the chain, then it can use it and manipulate it. As a result, every one of these requests just returns an incoming connection, which is basically a structure that has the structure that we already showed with all the IP addresses, context information, depending, of course, on your use case. I don't have much time. With the SDK, we currently have a couple of predefined composables. So as we said, one of them is the client, then we have the connection. We have IP address management and monitoring. Now, a little bit about IP address management. It essentially is a layer that is pre-configured with a subnet, and then it splits it into smaller /30 chunks for IPv4. It also supports IPv6, and kind of distributes IPs for all the incoming connections, for all the point-to-point connections. This, of course, is optional. It's not bind to network service mesh if you want to use IP connectivity. This is the composable that you should put in your endpoints. Explained like this, things probably look a bit scary and probably not really clear, but we have in our network service mesh examples repo on GitHub, we have a couple of examples. We have simple SMP responder, which is just a couple of containers sending pings to each other. We have the same thing implemented with MEMIF interfaces based on VPP running as a CNF. We have the Envoy interceptor, which Fred is going to show in 2 minutes. We have a proxy, which is essentially a gateway, a kind of HTTP reverse gateway, HTTP reverse proxy, which serves as a gateway to network service mesh from the HTTP world. And we have the secure internet, which is essentially, if you have seen already our story about Sarah and her VPN problems. And here is the Envoy.
Yeah, so to finish this up, let me hand this to you. Yeah, so to finish this up, one of the things that we did recently is we added in Envoy support, and so one of the reasons that we did this is Envoy is layer 4, layer 7, so it's probably more about how do you connect to an Envoy system. And so historically, when you run Envoy like in Istio or so on, you get a bunch of sidecars and then that exist, and you run them alongside with that. So what we're looking at is, well, what if that Envoy was something that was part of your infrastructure itself, and you connect it to Envoy, and rather than setting up an Envoy with each instance. And so with this, we created a simple Envoy configuration. So this one in our example, so this is actually in our repository, so you can actually get it and run it and see it connect to Envoy with the Envoy echo. So when you open up a TCP/IP connection with it, it'll then respond back with anything that you write to it. And the way that this ends up looking in the destination is that the default match is empty, so it's a wildcard, and then the destination in this scenario is there's a slight typo. We put Nginx. We need to stick Envoy in there. Apologies. And it works in the same way. It establishes the init container, gets you access to the Envoy. Envoy does not support shared memory interface at this time. So one of the things that we do is we've used the IP tables out of Envoy in order to reconfigure in order to redirect everything to the port. And so I don't think we have time to show it at the moment, though, do we?
No, yeah.
So
Just announce the meetup.
yeah, so we're going to be meeting today at 2:30 as well. So if you have any questions on this, like come over and ask us. The three of us should all be there. Nikolay is going to also talk about it at his booth on Thursday from 10:30 to 12:30. So yeah, feel free to talk with any of us afterwards. If you have any questions on it or you want any clarifications or so on, we'll be happy to talk to you about it. Thank you.